Hi, welcome to our presentation. I'm Daeyoung Park from Seoul National University. Today, I will present our work SnuQS, scaling quantum circuit simulation using storage devices. In this presentation, I'll talk about a full-state quantum circuit simulation framework called SnuQS. SnuQS is a cost-effective and scalable quantum circuit simulation framework that exploits storage devices such as HDDs and NVMe SSDs enlarge the available main memory capacity at a small cost, and applies many optimization techniques for performance. This is joint work with collaborators Heehoon Kim, Jinpyo Kim, Taehyun Kim, and my advisor Jaejin from Seoul National University. Quantum computing is a new computing paradigm that exploits quantum mechanical phenomena. Quantum computers are expected to change our world by making certain intractable problems solvable, such as machine learning and optimization problems. In recent years, many prototype quantum computers have been developed, but it's far away from stable quantum computers. We are still in the NISQ era, in which tens to hundreds qubit quantum computers are available, but still vulnerable to noise. In the NISQ era, the only way to prepare for the quantum future is to simulate quantum systems. A quantum circuit simulator mimics a quantum computer to develop, test, and verify quantum algorithms. In this sense, quantum circuit simulation is the most important technology in the quantum computing software ecosystem. There are two types of quantum circuit simulation method: full-state simulation and amplitude sampling. The table summarizes the differences between them. The full-state simulation uses a Schrödinger-style algorithm, and the amplitude sampling uses a tensor network contraction algorithm. The full-state simulation is memory-intensive, and the amplitude sampling is computation-intensive. In addition, each has its own preparing circuits and simulation goal. SnuQS focuses on the full-state simulation, since it can mimic a real quantum computer easily. It's well known that quantum circuit simulation is an extremely hard problem. The main challenge in the full-state simulation is the exponential growth of memory space. While an n-bit classical system requires O of n memory space to store the classical state, an n-qubit quantum circuit requires O of 2 to the n memory space to store the quantum state. The table on the bottom lists the top 4 supercomputers as of November 2021 in top 500 with their estimated qubit limit. Note that each has more than 1 petabyte of main memory, but the simulation limit is less than 50 qubits. Previous work used large-scale supercomputers to handle the exponential growth problem. The size of supercomputers ranges from thousands to tens of thousands of nodes with petabyte-scale memory space. However, large-scale clusters have low accessibility and high cost. It's hard for an average user to access such supercomputers for quantum circuit simulation. Also, building and running large-scale clusters is expensive, as well as they consume a tremendous amount of energy. Instead, SnuQS leverages storage devices such as HDDs and NVMe SSDs to scale quantum circuit simulation. Instead of DRAM, it exploits chip storage devices as secondary memory space. Instead of using thousands of nodes, SnuQS can simulate large quantum circuits on a single node. SnuQS is a shorthand for Seoul National University quantum simulator using storage devices. SnuQS uses memory overlays for the full-state simulation using storage devices. It divides storage space into blocks and loads a block into the main memory when necessary. Memory overlays require efficient data layout management method. SnuQS formalizes a quantum amplitude layout and manages overlays in a systematic way. SnuQS proposes an automatic sub-circuit partitioning technique that partitions a quantum circuit into sub-circuits. It partitions depending on the gate parents of the input circuit. Each sub-circuit uses data from the storage devices to apply gates. To transform the amplitude layout efficiently during simulation, SnuQS proposes a 3-step layout transformation algorithm. It eliminates unnecessary I/O and improves effective I/O bandwidth by decomposing layout transformation in 3 steps. SnuQS also optimizes simulation time using parallelism, exploits I/O and data parallelism, and computation communication overlapping. Finally, SnuQS proposes a storage system architecture with a high I/O bandwidth of storage devices. The system can provide maximum bandwidth for many storage devices. We have built the storage system and evaluated SnuQS performance on it. The figure shows the SnuQS framework. SnuQS takes a cont'd circuit and the system description as input and produces the final state in the storage space as a result. The cont'd circuit optimizer analyzes and transforms those input circuits into optimized circuits. The full-state simulation library implements the operation of each gate. It parallelizes and vectorizes the gate operations. The runtime system manages I/O and GPU commands. Finally, the simulator implements memory overlays by calling the runtime system interface and simulate the cont'd circuit by calling the gate functions. Figure A on the right shows a 3-qubit cont'd circuit with 7 quantum gates. The cap factor is the standard way of representing qubit states. Each qubit can be in the superposition of cat 0, cat 1, like alpha 0, cat 0 plus alpha 1, cat 1. Here, alpha 0 and 1 are complex numbers called amplitudes. When there are 2 qubits, there are 4 amplitudes. In general, n qubits require 2 to the n complex amplitudes. Each quantum gate is a unitary matrix. Each edge gate in the figure A is a 1-qubit gate because it operates on a single qubit. Each siege gate is a 2-qubit gate because it operates on 2 qubits. Each gate in a cont'd circuit depends on the previous gate operation on the same target qubit. We can build gate dependence graph is in the figure B. We define the depth of a cont'd circuit to be the number of nodes in the longest path in the dependence graph. Quantum gate operations works as follows. To apply a single qubit gate, we multiply the associated 2x2 unitary matrix to every pair of amplitudes. The subscript indices of each pair are the same except for the target qubit index. For example, when the Pauli X gate is applied on a qubit Q0, the amplitude pair of alpha 00 and alpha 01 swap their positions, and the amplitude pair of alpha 10 and alpha 11 does the same. Similarly, to apply a 2-qubit gate, we multiply the associated 4x4 unitary matrix to every quadruple of amplitudes. The subscript indices of each quadruple are the same except for the 2 target qubit indices. For example, when the CNAT gate is applied on qubit Q1 and Q2, the matrix is applied to the amplitude quadruple of alpha 000, alpha 010, alpha 100, and alpha 110. 2-qubit controlled gates and diagonal gates can be optimized further by omitting unnecessary computations. Then, the question is how we can simulate quantum circuits using storage devices. In particular, we have to store amplitude in storage devices and lose them when necessary. But the quantum gates determine which amplitude to load into memory. To apply a quantum gate, each pair or quadruple of amplitudes corresponding to the target qubit has to be in the main memory at the same time. SnuQS takes the memory overlay approach as shown in the figure. It divides storage device into multiple blocks and transfers a block replacing data in the memory space. The simulator explicitly transfers the blocks when necessary. A typical way to enlarge memory space is to use the virtual memory system called swapping. However, it suffers from performance degradation due to the I/O bandwidth underutilization and the overhead of printed page. In this sense, SnuQS uses overlay-based memory management technique for better performance. Essence of memory overlays is a systematic way of data layer management. We formalize the data layer for quantum circuit using qubit permutations. A qubit index is the unique identifier of each qubit. We denote a qubit with Q substituted with its index like Q0, Q1, Q2, and Q3. Qubit permutation represents the permutation among n factorial ways of ordering n qubits. We denote the permutation as an ordered sequence of qubit indices enclosed in a parenthesis as the permutation Q2, Q1, Q3, and Q0. A qubit position with respect to a qubit permutation pi indicates where each qubit is located in the permutation. For example, the qubit permutations of Q0, Q1, Q2, and Q3 are 0, 2, 3, and 1, respectively. An amplitude layout is an order of amplitude. In fact, a qubit permutation can determine the specific amplitude layout. For example, the location of each amplitude is stored as in the figure. Suppose the main memory can store 2 to the m amplitude. We categorize qubits in two classes, depending on their positions in a permutation. If a qubit's position with respect to a permutation pi is less than m, the qubit is local with respect to the permutation pi. Otherwise, it's non-local. For example, suppose m is 3 and a permutation pi is Q2, Q1, Q3, and Q0. Then, Q1 and Q3 and Q0 are local qubits, and Q2 is a non-local qubit. We can distinguish quantum gates in a similar way. A quantum gate is local with respect to a permutation pi if its target qubits are local with respect to the permutation pi. Otherwise, the gate is non-local. For example, in the quantum circuit on the slide, G1, G2, G3, G4, and CNA1 gates in the red box are local gates. CNA2 and G5 gates in the blue box is a non-local gate. Note that G6 is a local gate but depends on a non-local gate CNA2 and hence cannot be executed before the CNA2 gate. Based on the amplitude and layout formalism, SnuQS partitions a quantum circuit into sub-circuits. In SnuQS, each sub-circuit has only local gates with respect to a permutation. Suppose we are given a quantum circuit as in the figure. It's a 4-qubit circuit and we assume that the memory can store 8 amplitudes. Here, Q1, Q3, Q0 are local qubits. We can partition the circuit into two sub-circuits as shown in the figure on the right. The second sub-circuit follows a new permutation Q3, Q1, Q2, and Q0. Its gate in any sub-circuit is local with respect to the associated permutation. Thus, all gates can be applied if the amplitude layout follows the associated permutation in each sub-circuit. The general sub-circuit partitioning algorithm is simple. It starts with the identity permutation pi. Given the permutation pi, it finds all local gates before the first non-local with respect to the permutation pi. The found gates become a sub-circuit. Then, it selects a new permutation pi and repeat until there is no gate to process. To select the next permutation and reduce the number of sub-circuits, we use a simple heuristic algorithm based on gate patterns. Now, I will explain the SnuQS simulation algorithm. With the partitioned sub-circuits and their associated permutations, SnuQS simulation algorithm runs as follows. Suppose that we are given a 4-qubit quantum circuit and the main memory can store 8 amplitudes. It simulates each sub-circuit one by one until all sub-circuits are processed. For each sub-circuit, it iterates 2 iterations where each iteration updates 8 amplitudes at a time. For now, the first sub-circuit is associated with the permutation Q2, Q1, Q3, and Q0. For the first iteration of sub-circuit Q1, it lists 8 consecutive amplitudes with respect to the current permutation from the storage space to the main memory. Then, it applies all gates in the sub-circuit in the main memory. Finally, it writes back the updated amplitude to the storage space. For the second iteration, it lists the next 8 consecutive amplitudes with respect to the current permutation. Then, It applies gates and write back the updated amplitude to the storage space as before. Then SnuQS changes the amplitude layout for the new permutation Q3, Q1, Q2, and Q0. SnuQS optimizes the layout transformation using three-step layout transformation method, which will be discussed soon. For now, we assume that the layout has been changed accordingly. The second sub-circuit is associated with the permutation Q2, Q1, Q3, and Q0. The remaining steps are the same as before. For the first iteration of the second sub-circuit, allows 8 consecutive amplitude from the storage space to the main memory. Then, it applies OR gates in the sub-circuit in the main memory. Finally, it writes back the updated amplitude to the storage space. For the second iteration, it raise the next 8 consecutive amplitude, relates back to the current permutation. It applies gates and write back the updated amplitude to the storage space again. Now, I'll explain the efficient layout transformation technique called three-step layout transformation. We decompose a layout transformation into the first in-memory transformation, and the second block index transformation, and the final in-memory transformation. Through the three-step layout transformation, we can ensure the minimum block size is large enough to exploit I/O bandwidth efficiently. Suppose we want to transform from the layout Q2, Q1, Q3, and Q0 to Q3, Q1, Q2, and Q0. We also suppose that the minimal block I/O size is 4 amplitude instead of 1 amplitude. At the start, the amplitude corresponding to each stage are stored in the order shown in the figure on the left. The top represents the order's 0 location, and each amplitude is 16 bytes. Using the first in-memory transformation, we can change the layout from Q2, Q1, Q3, and Q0 to Q2, Q3, Q1, and Q0. In-memory transformations are executed in place using multiple swap operations. In this example, the locations of third and fourth amplitude are swapped with fifth and sixth amplitude. For performance, the first in-memory transformation are performed at the end of each iteration of sub-circuit 1 before the write back to the storage space. Next step is the block index transformation. Reorder amplitudes in the granularity of array blocks as shown in the figure. Using the block index transformation, we change the layout from Q2, Q3, Q1, and Q0 to Q3, Q2, Q1, and Q0. Block index transformation can be performed efficiently by bookkeeping the addresses of blocks without any I/O. Block index transformation occurs when you read blocks at the first of each iteration of the sub-circuit 2. Using the final in-memory transformation, the layout transforms into our target layout. For performance, the final in-memory transformation is performed at the start of each iteration of sub-circuit 2 after the block index transformation. Now I explain the SnuQS implementation. The figure shows the SnuQS runtime system. It consists of I/O and GPU subsystems. Both have the request coverage queue pairs and the corresponding dispatcher thread. Each dispatcher thread keeps pulling the request queue. When a command is enqueued, it executes the command and re-enqueue it to the completion queue. It simulates the circuit by continuously enqueuing either gate operation, CPU-GPU communication, and I/O operation. The I/O subsystem manages I/O operations using multiple I/O handler threads. An I/O handler resides in a CPU core with no migration. We use up to 64 I/O handlers, which is equal to the number of CPU cores. The handler executes I/O operations using Linux I/O link system calls. The GPU subsystem works similar to the I/O subsystem, but dispatcher thread executes the command using the CUDA runtime. SnuQS also optimizes performance using many techniques. It exploits I/O parallelism by accessing storage devices simultaneously. It configures storage devices like RAID 0 but uses a larger block size for higher I/O bandwidth. It also exploits data parallelism by parallelizing gate operations using OpenMP per CPU and CUDA per GPU. SnuQS tries to maximize the overlaps between computation, CPU-GPU communication, and I/O. SnuQS always prepatches the necessary amplitude for the next iteration. Finally, it balances the computation workload between sub-circuits by scheduling gates. The target system specification is shown in the above table. The system consists of a multiple CPU, 4 GPUs, and many storage devices. The exact system architecture is shown in the below figure. For the evaluation, we use two configurations, HDD configuration and NVMe configuration. The storage system architecture is designed deliberately to accommodate the maximum bandwidth of storage devices. Each HDD provides a maximum bandwidth of 0.2 GB per second. Each SAS3 interface can accommodate 20 HDDs. Each RAID card on PCIe 4.8 lanes long has two SAS3 ports and can accommodate 40 HDDs. The system has two RAID cards and can accommodate 8 HDDs in total. For the NVMe configuration, we use 10 NVMe's directly attached to M.2 and PCIe bus. The evaluation is based on two benchmarks and two configurations. The two benchmarks are quantum Fourier transformation, called QFT, and quantum supremacy circuits, called QSC. QFT is the most widely used quantum algorithm. It has linearly increasing depth to the number of qubits. QSC is the de facto standard benchmark to measure quantum circuit simulation performance. The figure on the right shows an example of test 26 7x6 quantum supremacy circuit. We use multiple instances of the two benchmarks with different number of qubits. If not mentioned explicitly, we simulate using double precision floating point formats and use 4 GPUs in all experiments. The HDD configuration consists of 82 TB HDDs, and the NVMe configuration consists of 10 4 TB NVMe SSDs. For the HDD configuration, we simulate up to 42 qubits. For the NVMe configuration, we simulate up to 39 qubits. We denote each benchmark circuit by its name, followed by the number of qubits and each steps. For example, QSC 4250 stands for depth 50 42 qubit QSC. The table on the right shows the details of circuits and their simulation time. The results show that we can simulate 42 qubit quantum circuits within reasonable time using a single load with HDDs. Simulation of QSC 4250 using HDDs can be finished within a day. The simulation of QFT 4284 can be finished within 8 hours. We can boost the simulation using faster storage devices, in this case NVMe SSDs. The result reveals that NVMe SSDs show significant speedup over HDDs. In QSC 3950 is finished within an hour, and QFT 3978 within 10 minutes. A simple calculation shows that the speedup of NVMe SSDs over HDDs is n-2. SnuQS also robust to deep circuits. In particular, QFTs are deep circuit, and we simulate up to depth 84 circuits. Also, the simulation time of QSC 4250 is almost twice as much as QSC 4226, showing that the simulation time is almost linearly proportional to the circuit depth. Finally, SnuQS is cost-effective using storage devices instead of DRAM. The cost of DDR for DRAM, NVMe, and HDD per gigabyte are 6.01, 0.19, and 0.02 respectively. We can build a system with the same qubit limits using 31.6 times lower cost of NVMe SSDs and 300 times 0.5 lower cost of HDDs. Even though the DRAM-based system is faster, the slowdown of SnuQS is tolerable considering the huge cost effectiveness. Now we analyze the scalability of SnuQS by defining the size of quantum circuits. The figure A and B shows the per gate simulation time by varying the number of qubits in the benchmarks. Since each circuit of different size has a different number of gates, we use the per gate execution time instead of simulation time. The per gate execution time on the y-axis is in the log scale. Each figure shows a nice straight curve, which shows that the simulation time is exponentially proportional to the number of qubits. There is a slowdown between the 34 qubit and 35 qubit simulation, especially for HDDs in figure A. This is the point where the state does not fit into the main memory. We also compare simulations on the CPU and GPU system using 42 qubit benchmarks. The table on the top shows the simulation time using CPU. The GPU simulation outperforms the CPU simulation in all cases. Using the Runtime model, we find that speedup comes from the memory bandwidth gap. Gate operations are memory bound and GPUs have much higher memory bandwidth than CPU. We also compare the memory overlays of SnuQS and the demand paging by the operating system. We simulate hard-mode and cont'd gate using the Qubit and QS simulators and compare them with SnuQS. We use the CPU system in this experiment, and the total size of the virtual memory space is set to 32 TB to support 41 qubits. SnuQS achieves more than 70 times speedup. Paging takes huge overhead and cannot exploit full I/O bandwidth. Finally, we compare the simulation time of 30-qubit quantum circuits to the state-of-the-art quantum simulators using two benchmarks. The table on the bottom shows that SnuQS is comparable to Cirq and outperforms other simulators. It shows that SnuQS is fast even for small circuits that does not require I/O. We compare SnuQS with the state-of-the-art full-state simulator on Core 2, say Core. It's hard to compare them directly because they have different system configurations. So we compare their floating point efficiency, called FP efficiency, and single node execution time based on analytic estimation. The table shows the comparison results. Core uses 4,096 nodes, each of which has an Intel Xeon Pi 7250. The estimation shows that SnuQS achieves much better LP efficiency than Core. Core achieves 2.39% of LP efficiency, while SnuQS achieves 30.29%. We also compare the single node execution time. We define the single node execution time to be the minimal simulation time when we assume a single node configuration for both Core and SnuQS. A conservative estimation shows that single node execution time of Core is 25.52 hours. On the contrary, SnuQS takes 9.81 hours with GPUs and HDDs. SnuQS achieves better single node performance than the state-of-the-art. SnuQS outperforms the state-of-the-art for the following two reasons. As seen before, gate operations are memory bound and GPU memory bandwidth larger than MC-DRAM memory bandwidth. Note that the SOTA simulator uses the unpackaged MC-DRAM as a cache of the main memory. The other reason is that SnuQS overrides computation, CPU-GPU communication, and I/O using triple buffering, while the SOTA simulator does not apply the same technique. In this presentation, we propose SnuQS, an optimized quantum circuit simulation framework using storage devices. It manages memory overhead efficiently, reduces I/O overhead, and provides cost-effective solution to large-scale quantum circuit simulation. The proposed method scales well, and the simulation time is very predictable. We expect that SnuQS can be extended easily using more storage devices. We also expect that the proposed method can be easily applied to other systems, for example, small clusters to simulate petabyte-scale quantum circuits. Thank you for listening my presentation.